Here again, we made re-emphasize the points that we made earlier. When you have joint distribution, you can compute marginal probability. You can compute conditional probability. It's a full model. You can answer any questions related to this. There are 3 types of queries. All arbitrary queries can be answered. Diagnosis type, cause and symptom. So given cause, given symptom, figure out what was the cause. This is a diagnostic type. Prediction type, we have cause, predict the result. Classification, it's just a different way to say the above things, that you have data and can belong to multiple classes, and you find the maximum probability for certain class. That's your class label. All those, we can actually formulate that query into a general case query. So in any query, we can formulate it this way. We have evidence variable, we have query variable, we have hidden variable. So x to xn are all our variables. So all those combined, E, Q, H combined is all covered, all our variables in this graph, in the network. So using one example, if we want all those E1 to EK certain conditions and predict something, the chance for this thing to happen, this is a conditional probability, remember? So for conditional probability, how we compute that, we select the entries consistent with the evidence, with the condition E1 to EK. And then they're bound to be hidden variables, because we probably won't, in our queries, won't cover all the variables. For example, we can say in our earlier example, we know cause 1 to predict this. We're not mentioning cause 1, symptom 1, and symptom 2. So those will be hidden variables. In those, we will deal with those hidden variables. Remember, when we do conditional marginal probability, we sum out those hidden variables. So here, so for those hidden variable h1 to hr, we have to explicitly list them and enumerate through them to sum up all the probabilities. With that, the final step to get the conditional probability is just to normalize. And we also went through that at the beginning. So this just normalize, the purpose of normalization is to make sure all the probabilities sum up to 1, so that we know that our final result is a normal, is a probability distribution. So given unlimited resources, have 1 minute, we can go through this example. Given unlimited time, inference in a network is easy. We can just look at this as example. Because the step, as we can see, really, we only need to do this. And the normalization is really very simple, just a sum and divided by how many that we have. This Z is, for every Q, we sum up all the probability and then normalize divided by 1 to get the probability distribution. So therefore here we really want to just compute this joint probability. And this example to show how to compute the joint probability. So we have hidden variables, E and A were not here, so we have to sum over all those hidden variables. This is a probability given our chain rule and the dependence on the parents. We'll have B without parents, E without parents, A conditioned on B and E, and P conditioned, P is the J term, conditioned on A, M conditioned on A. Once we have that, we will have to plug in all different values of E and A to sum out all the possibilities of the hidden variables. So this is all that thing that we need to find. So after we find out this, for the B terms, we have positive B and negative B, and we will plug those in and find individual probabilities and normalize those. That will give us the joint probability, the probability distribution for this. When this happens, what's the probability for B to be positive or negative, or for B to happen or not? Did I lost you? Tell me what questions do you have? I know we're running out of time, but I will try to figure out some examples to help you clarify some of the issues next class. The following part, what we're gonna learn is to basically a trick to simplify this to make it more efficient. But that's not crucially important. All we wanted to, the point that we want to make now is, given this the structure of the network, the conditional independence given the parent node is independent of all its non-sibling nodes. With that, we can actually use this function to compute the joint probability. Now, with joint probability, we can do everything we need to do, all sorts of predictions. The challenging part, although we know that all the inferences can be done, computationally, it can be very, very time consuming, because a lot of times when we ask a query, the query only involves a few variables in the network. Vast majority of the variables in the network are hidden. And for those hidden variables, we have to actually enumerate their every conditions and have this big sum to find the final probability distribution for this query. To speed up that, a method called variable elimination has been used. The idea is very simple. So when we need to enumerate all those hidden variables, we observe that some hidden variables are not related to all the terms. So based on this rule that we know in sum, we can take out, we can distribute this E to the terms that has E as part of it. So this can dramatically reduce how many terms. We don't actually need to enumerate all the E possibility cardinality of E for the rest of those terms. We only need to do that for this smaller section. So this calls summing out. After E is summing out, we eliminate the variable E. You don't actually need to memorize this, just an idea. How can we make reasoning inferences quick enough in practical use using Bayesian leaf network.